to empty, the recent deleted ones. So we're on to question 4. We're on to question 4 now. The situation for question 4 is nice and familiar. It's just another conical pendulum. We've got these lengths here. We've got a 40 and a 25. So that is where, what are we talking about? The string is tethered. So we've got a tension going up there. We've got the mass of the object here. This, of course, is the direction of the acceleration. So our circle is a horizontal circle going around this way. We have got angle at the top. So my right angle triangle to work out the lengths. I've got 25, I'll put theta there, and 40. So it means that that length there, it's a slightly awkward 1,600 minus 625, square root of that, root 975, which is 5 root 39. That means that our sine is a rather awkward 5 root 39 over 40, or root 39 over 8. Cosine's a little bit happier. That's 25 over 40, so that's 5/8. Okay, so to find the tension in the string, first step, always resolve vertically. It's in equilibrium. I know the forces up have to balance the forces down. I have got this alternate angle here. I have got an angle there of theta. So I have got the cosine component. It's going to be t cos theta going up, and that is equal to mg going down. Cos theta is 5/8, so t multiplied by 5/8 equals mg, which makes t equal to 8 mg over 5. And of course we had to evaluate this, didn't we? I know what the mass is. That's 25 grams, so 8 times by 0.025 has to be in kilograms, of course, all divided by 5. And that gives an answer, 0.392 newtons. Second part, acceleration. Acceleration, we're using F equals ma. Of course, we have got to resolve in that direction. We're going towards the centre of the circle. Normally we have to kind of put in our speed or angular speed in there, but this is just leave it as it is and find the acceleration. We only have one force acting towards the centre, mg, the weight is perpendicular, and that's the other component of the t. We've just had the cosine, so of course it's going to be the sine, and yep, just check that component is opposite my angle there, so it's going to be the sine component. T sine theta is equal to mass times by the acceleration. T is equal to 0.392 multiplied by sine theta, which is the root 39 over 8, equals m, 0.025a. Divide all of that by 0.025 and I get an acceleration 12.24 meters per second squared. So now for part 3, we can put that into speed. I know that acceleration is v squared over r. So v squared is r times by a. R, that's this 5 root 39. 5 root 39 multiplied by 12.24. That gets me a value for v squared of 382.2. So v square root of that, 19.55 meters per second. Now the last bit. Explain why the object can never move in a horizontal circle with the point of support, level with the point of support. So if you can imagine our initial situation, we had a theta up there and there was our mass. And of course that was the circle in which it was going in. That was my direction, this direction of the acceleration. Now imagine this kind of gradually moving up until it's here. So it's saying instead, imagine it moving around there. Now, a couple of ways you can do it then. You can think about it purely mathematically and say, right, for this to happen, when it's level, instead of the angle here being acute, that angle is going to be 90 degrees. If we use our expression here when we resolved vertically, we said that t cos theta is equal to mg. So in other words, t is mg over cos theta. If you put 90 in there, cos 90 is 0. mg divided by 0, that's undefined. So, of course, that can't exist. Whenever you have something undefined, it means that there's something not right about it. That would get you the marks looking at it purely mathematically. Or you could think about what's happening, actually with the situation. For it to be at this level, for it to stay in that horizontal plane, it of course has to be in equilibrium vertically. It can't stay in that level plane if the forces going up and down aren't balanced. So if we resolve in this direction, we can see that we've got mg acting down, but there's nothing to balance it with. Before we had a component of the tension, but of course the tension is all going this way. So there is no force to balance against the tension. So it's not in equilibrium, which means it can't be going around in that horizontal circle. Okay, so question 4. Shall we move straight on to question 5? Let's see. I think question 5 is a little bit of a longer one. It's got an asterisk. It's the first of the asterisk questions, but as I've said, this is something that, all of these bits here are on the specification for year 12. So there's nothing here that you wouldn't have been asked to do had you been doing the exam. So a particle of mass m is released from rest at the point on the surface of a fixed smooth sphere. The radius OA is inclined at an angle of 45 degrees to the upward vertical. Okay, so what often happens in these situations, you have got a particle, at the top of the sphere, it's released from rest and, it kind of heads over here and at some point falls off. But actually what's happening here is it's being released from rest at point A. It's on the surface, but it's not at the very top. The centre is at 0. And it's being released at a point A where A or OA is at 45 degrees to the upward vertical. So if we draw the upward vertical in, which is that length, 45 degrees, it's actually over here. So what we've got, that is our starting point. Okay, and this is why this question is a little bit more awkward, because of that slightly bizarre starting point. So there I've got 45 degrees. It's being released from rest there. So actually, you can imagine it's not going to be hugging that surface of the sphere for very much longer until it falls off. Show that while P remains in contact, the reaction between... Okay. So I am going to think about and call another point here. So this is going to be a general point, but in time I'll come to think of that as the point where it falls off. So we've got another angle here. Again, if we measured that from the upwards vertical. So I've got two different overlapping angles here. So it means it's a bit more awkward when I think about my potential energies. It's a vertical circle, so we need to be considering a level from which to take all our points. I don't know, could take the top. If I take the top, then all the distances would be negative, which is a little bit awkward. So I think taking, I don't normally do this, but I think for this one, I'm going to call 0 the centre of the circle, where h is equal to 0. So I'd have to work out some lengths. At A, I have got this triangle here. So I've got this triangle here. I know that the radius, no, I don't know what the radius is. Should we call it A? Quite often it's called A. That's my radius. This is 45. Of course, I've got an isosceles triangle. But this length here would be A sine, because it's opposite. Sine 45, root 2 over 2 or 1 over root 2. Let's have A times by 1 over root 2, so that's A over root 2. This length here would be A cos 45. It is the adjacent component, but it's isosceles. Sine 45 is cos 45, so of course that's A over root 2. I'm also going to need this height here, aren't we, for the P triangle. So this is my triangle for A, this is my triangle for P. That is still A, but now this is theta. So we can use that as a template. It's going to be A sine theta and A cos theta. So when I come to write down my energies, I'm going to be using A cos theta as the height for P, and then A over root 2 as the height when it's at A. So I'm going to do my energies, can do my energies now. So at A, I have got gravitational potential energy plus kinetic energy. That is equal to mg multiplied by h, which is A cos 45 or A over root 2. Plus my kinetic energy. Do I know what V is? Half mv squared. It is released from rest, so V equals 0. So the energy there is just mga over root 2. At P, my potential energy plus kinetic energy is equal to mg. The height here, remember we're measuring against 0, the height there is just the A cos theta plus a half m, and here of course it will have some velocity. Mga cos theta plus a half mv squared. Using then conservation of energy, equate those two. Mga over root 2 equals mga cos theta plus half mv squared. M's go, I'm sure you're quite used to that now. I've got that 2, let's double everything. 2ga over root 2 is equal to 2ga cos theta plus v squared. So that makes v squared equal to 2g over root 2. 2 over root 2, of course, is root 2. So root 2 ga, and then I'm putting that onto the side, minus 2ga cos theta. So v squared is ga root 2 minus 2 cos theta. So that is an expression that I'm going to use for the next bit for my energies. Sorry, for my resolving. So I've got an expression for the velocity. Let's look at what's happening with my resolving. So I want to resolve towards the centre of the circle. I need a diagram. See, I'm just really lost without my diagram. Where is it? It's not there, is it? My circle is here. There is my particle. I've got the weight coming down, and there I've got my force, which of course is going to be a reaction force. It is sitting on the surface, and that reaction force is in the same direction as the centre, so that is the centre 0. I want to resolve towards the centre of the circle. I'm using F equals MA. I think this is the first one that we've done in this bunch of questions that has got more than one force acting towards the centre. Apologies if I'm wrong, but of course you've got the weight component heading inwards, and then you've got the normal reaction force going in the opposite direction. Where was theta? I've lost theta. So theta, of course, is this angle here, which makes this also theta. So if I think about it, that's the hypotenuse. That component is adjacent to theta. So I've got mg cos theta heading towards the circle, and my forces going away from the centre of the circle are. So that's my resultant force in the direction of motion, and that has got to be equal to m times by a. The a I'm going to use, of course, is v squared over r, because that's the expression I've got in the previous part of the question, is equal to m v squared over r. The v squared that I had from before, that expression there. So if we go down there, mg cos theta minus r is equal to m ga root 2 minus 2 cos theta, all divided by r, and r is, of course, a. Those a's cancel. So what I've done there, I've just done it for a general point P. So remember kind of our point here. So for all points P as it comes down, and that's whether we're kind of there or whether we're further down there. But what the question's asking, show that while P remains in contact with the sphere, we have the normal reaction is equal to this here. So we've got to kind of expand that. Apologies, we've got to kind of carry on and work on this. I'm thinking ahead to the next bit of the question. That a is gone, so I need to expand that. So I've got root 2 mg minus 2 mg cos theta. I want to make r the subject, so I'll pop that over there, those two things onto there. So it'll be mg cos theta minus the root 2 mg plus that one, 2 mg cos theta, and that's equal to r. These two combine to give 3 mg cos theta minus root 2 mg. Factor out the mg and we're left with 3 cos theta minus root 2. And yeah, that is what we kind of need. Apologies for my little kind of diversion earlier. So now on to part 2. Find to the nearest degree the value of theta when P leaves the surface. So if I go back to this diagram here, what I've got here is an expression when it's still in contact, but at some point here it's going to fall off, and when it falls off, that's because it loses its contact. It means that the contact force here goes to 0. So when P leaves the surface, r is equal to 0. So I'm just going to use that expression there and substitute 0 in. Of course, I know that the mass and g are non-zero, so as mg isn't 0, it means that this has to be 0. So 3 cos theta minus root 2 is 0. So 3 cos theta is root 2 cos theta is root 2 over 3. And if we inverse cos root 2 over 3, we get an angle of 61.9 degrees. Okay, so I thought that one was hard. That one was hard sorting out what was going on there. It's algebraic, but you know, a lot of them are algebraic. It looks if it doesn't give you enough information, but then, you know, lots of things cancel. Having the two different forces here that you need to resolve when you're looking at F equals ma, it's so easy to miss out on one of these and, of course, end up with something that's not correct.